Hey all, just doing a quick audio test. If you guys can hear me, go ahead and mention something in the chat room. We have about 4 minutes before we're going to get started. So sit tight and we will go live, but definitely let me know if you guys can hear me in the chat room. Excited to do this. Well, hello everyone. Looks like the stream's working, audio's working. Hello, welcome. Welcome to the first of a series of streams and live lessons I'm going to be doing, rather, on lessons I'm going to be doing on OSPF. Glad you guys can join us. The plan was to essentially run through some of the curriculum I've already put together on OSPF. These will one day become, their own professionally polished and edited videos. But for now, I figured why not go through the content live with you all, just taking to get some feedback on the curriculum to see how it's going. So a few weeks ago, I asked you guys what you guys wanted to learn next. Actually, this really started almost at the end of last year. I asked what you guys wanted to learn next, and OSPF was at the top of the list. So that's where we are now. And then a few weeks ago from today, I asked you guys how deep you wanted to go with OSPF. And all of you said you want to go deep enough to make you a proficient engineer. So to that end, that's the goal of this particular series. We're going to be doing this in a few different modules. This is essentially going to be module 1. This is going to be kind of like high-level OSPF stuff, and then we'll get deeper and deeper and deeper as we continue to go. So look forward to some more of these live streams in the future. So if you're trying to study for the CCNA, today we'll probably cover, I would say, 85% of what you need for the CCNA. The whole series will cover everything and above what you need for the CCNA. If you're looking for the CCNP, the whole series will probably cover probably about 95% of what you actually need for the CCNP. That 5% remaining will probably be just a few things that Cisco thinks is very important for you to know that I don't think are that practical or necessary in the real world. So if you are studying for the CCNP, the complete series, once it's done, will definitely get you most of the way there, but you might have to do a little bit of memorization of a few extra things that Cisco might want you to do. So that's kind of the plan for the day. Yeah, and so today, actually in this live stream, a large part of why I'm presenting this to you in the live stream is to actually get feedback on the content. So what we'll do is we'll do a lesson, and then we'll stop for a minute, and I'll ask you guys how it went, what you guys thought of the content, whether things could be improved or whether the thing's pretty good as it is. So that's the plan for the day. So again, this is going to be a very feedback-oriented session. I'm presenting this to you and then asking for your feedback, your thoughts, so you can kind of guide and shape the way this goes in the long term. So yeah, so please be involved in the chat. If you're watching this on replay afterwards, please continue to provide the feedback in the comments. All that will help. I take that to heart. The goal, again, is to make this the ultimate OSPF series for you and future engineers out there. With that said, let me make sure I'm not missing any chat room questions. Cool. Glad you guys are interested. Excited to have Chris join us. Actually, Chris is a friend. He has a channel with some of the best TCP related content. So if you're interested in TCP related content, definitely check out Chris Creer's channel. I'm sure Chris, if you want to throw a link to your channel in the chat room, you're welcome to. Otherwise, I don't see any questions, so let's get into it. Okay. So we have about 6 lessons, I believe, to go through, 6 or 7 if I recall. And the last lesson is going to be a demonstration of everything we've learned throughout the series. So we're going to go through all the lessons, and then I'll prove everything we've learned on real routers and switches, well, through GNS3. That way it isn't just you taking my word for it on how things work. It's actually you seeing how things actually work to give you kind of refined knowledge on it. But with that said, we're going to start at a pretty high level. Audio, cool. We're going to start at a pretty high level and really just talk through, at the very beginning, just dynamic routing protocols in general. All right, so the purpose of a dynamic routing protocol is simply to have routers automatically share routes with each other. Now, we introduced the concept of dynamic routing when we talked about when we went through the networking fundamentals series, so specifically in this lesson, lesson 5A. We showed you this slide where we talked about the 3 different ways that routers have to populate their routing table. That's directly connected, static routes, and dynamic routes. And the purpose of this series is, of course, going to be focusing on dynamic routes with a focus on OSPF, of course. So in that lesson, we talked through how router 2 and router 1, if they're doing dynamic routes, are going to be sharing routes with one another. And there's many different ways for that to happen. That's what OSPF, BGP, ISIS, EIGRP, all of that. All of those are different ways that the routers will discover each other's presence, different information they'll share with each other. The purpose of this lesson, of course, is to cover OSPF. But if you're looking for kind of a foundation of networking before you get into this particular series, I would highly recommend the entire networking fundamentals series. You can access at pracnet.net/nf for networking fundamentals. This is probably the best place to start if you're trying to do anything network, is watch that particular series. With that said, let's talk about the different dynamic routing protocols that exist. So the main ones out there, RIP, EIGRP, OSPF, ISIS, and BGP. Now each of these can be categorized into different groups, and we're going to start by looking at the 2 sets of groups that they can be categorized within. So the first set of groups that they can be categorized within are IGPs and EGPs. So an IGP stands for an interior gateway protocol, whereas an EGP stands for an exterior gateway protocol. And these essentially differ in what they are best suited for. So to talk through them, we're going to use these particular topologies. So we have here we have company A with a bunch of routers that are meant to do dynamic routing with one another. And then here we have company B, same thing, meant to do dynamic routing with one another. Since these are two different companies, they can each be referred to as different autonomous systems. Now, the word autonomous system is pretty important, so I do want to give you a formal definition for it. An autonomous system, or an AS, is a set of routers or networks underneath a single administrative control. So since company A is different from company B, company A manages company A's routers and company B manages company B's routers. Therefore, those are two separate autonomous systems. With that in mind, we can now talk about IGPs. So an IGP's primary purpose is to share routes within an autonomous system, within an AS, within an autonomous system. IGPs are typically tuned for speed and responsiveness. The idea there is if, say, this router over here has a failure event and we need to reroute traffic through to the other router, we want all of these routers to instantly know that something happened and there's a change in the topology. Hence, an IGP is going to be your best bet for that. By comparison, a BG, we'll talk about that in a minute. Cool. So that's an IGP. Again, they're primarily tuned for speed and responsiveness. To talk about BGPs, by comparison, are primarily suited, EGPs are primarily suited for sharing routes between autonomous systems. Now, the primary EGP in use today, so again, EGP is the category, exterior gateway protocol, but really the only one that the entire internet uses at the moment is BGP, so you'll probably hear me say BGP and EGP using the same term, but really one's a category and one's a specific protocol. In any case, EGPs are meant to share routes between autonomous systems. To talk about that, we're going to add two ISPs, connect them in, and the way it's supposed to work, and again, since these ISPs are different entities, they are also their own autonomous system, and you would use something like BGP for company A to share its routes with ISP X. ISP X will share it with some other ISP, and then ISP Y will share it with company B. The major difference between EGPs and IGPs is EGPs are tuned for stability and security. So earlier we gave you the example of like something changing between these routers over here, right? And we want these routers to notify all the other routers in company A's network instantly so that they can quickly adjust to the new path the traffic is meant to take. Uh-oh, my face is in the way. Let's move my face. Yeah, better. Cool. So we want traffic changes within an IGP, within an autonomous system, to be updated, to update all the other routers instantly. The issue, though, is if there's a different path that these routers are going to take in company A, the rest of the internet doesn't really need to know about it. Either way, ISP X is still going to be using these links to get to company A's network. So you'll see that an EGP is suited for stability, is better tuned for stability, versus an IGP is better tuned for speed and responsiveness. Consider it isn't that there's one's better than the other. There's just different use cases, which makes one more appropriate for the other. And typically an EGP is for communication between autonomous systems. The other thing I'll mention down here is security. You can do some sort of route filtering with all the IGPs, with most of the IGPs, but not nearly to the degree that you can with BGP. BGP allows you to do so much control and fine tuning of how routes are accepted, what routes you send out, what metrics you send with the route, and so on. You need that sort of control if you're advertising routes to ISPs and to the entire internet. But most of the time with an IGP, you're not going to be doing all that much in sort of security. If these are all going to be participating in a dynamic routing protocol, they're all going to be sharing all the routes they know about with one another. Cool. So that is the categories of EGP and IGP. With that said, let's focus on the IGPs. We can categorize these four protocols into two separate categories. Those categories are distance vector and link state. So let's use this topology to talk through it, and we're going to talk about the link state protocols first, which is OSPF and ISIS. So link state protocols include, provide the routers with knowledge of the entire topology. So if router 5, and really all the routers in this topology, are doing a link state protocol with each other, router 5 is going to know that it's connected to router 6. And then router 5 is going to know that router 6 is connected to router 7, router 8, and router 9. And router 5 is going to know that router 7 and 8 are connected, and then router 8 and 9 are connected. And the same thing over here. They're going to know everything that's happening on this side of the network. The cost to that is that using a link state protocol is going to require more RAM and more CPU on router 5. But the benefit to that is that if something happens, router 5 is going to be better equipped to converge after a failure event. For example, if this link breaks, router 5 already knows that router 6 has a connection through router 8 to get to router 7, and so nothing new insofar as calculations and network discovery have to be done. It essentially already knows the backup path to a particular network. Oops, my face is in the way again. Yeah, that'll work. Let me know if my my face on the stream is covering something in the chat. My bad about that. Okay, in any case, back to where we were. Cool, so that's a link state protocol. So again, it requires more CPU and more RAM, but the benefit to that, right, is you get typically the faster convergence. Cool. So now let's talk about the distance vector protocols. And by the way, I see y'all's questions in the chat. I'll come back and go to the questions at the end of this lesson. So I'll definitely cover all of your questions. Please keep asking. So the way distance vector is different from link state is that distance vector protocols don't provide knowledge of the entire topology. They really only provide knowledge of the next hop. So if router 5 is doing distance vector along with all these other routers, router 5 is going to know that it's connected to router 4 and router 6, but it's not going to have any knowledge of what's happening on the other side of router 4 and router 6 respectively. All it's going to know is that somewhere on the other side of router 4 are these IP networks, and somewhere on the other side of router 6 are these 3 networks. So you see the benefit to that is that it means that compared to the link state protocols, running a distance vector protocol requires less RAM and less CPU. But as you can probably guess, since you don't have as much knowledge of the rest of the topology, it is going to be a bit slower to converge traditionally. Meaning, if router 5 sends a packet to knows to get to this network, it's going to send something router 4, and router 4 knows it's going to go this direction. If something happens to this link, router 4 is going to tell router 5 that it no longer has access to this network. Router 4 won't relearn access to that network until router 1 advertises to router 2 advertises to router 4 that it knows how to get to the 10.0.1 network, and then router 4 passes that on to router 5, and then router 5 will have regained access through the backup path to that particular network. So all that time, router 5 will have no connectivity to the 10.0.1 network. So that's the offset of distance vector versus link state. Now again, it isn't that one is always better than the other, right? It's always a trade-off, right? That's really the world of network engineering, is understanding both options, both sides of the trade-off, and making the best decision based upon what you're trying to do. Are you using older gear, or do you have a smaller simplistic technology? Then yeah, maybe you can, maybe you can get away with a distance vector protocol. Do you have a very complex network? Are you running an ISP grade network or an enterprise grade network? Then yeah, maybe you have better gear that can handle the additional RAM and CPU, and you'd rather pay the cost of additional RAM and CPU to get faster convergence. Again, it's all pros and cons. Now, I will mention, and actually someone else mentioned it in the chat, EIGRP has elements of link state protocols within it. So while if I'm being an absolutist about the categories, it does fall into the distance vector protocol, but more often it's referred to as a hybrid protocol or even an advanced distance vector protocol. That's a Cisco marketing term, because EIGRP does all the benefits of distance vector, meaning doesn't require as much RAM and CPU, but also some of the benefits of link state protocols. So EIGRP is kind of special in that regard. And yeah, and that takes care of the categorization of the different protocols that we wanted to talk about in this particular lesson. So again, we talked about the categories of IGPs and EGPs, and then we talked about the categories of link state and distance vector protocols. In the next lesson, we're going to go a little bit further into dynamic routing as we get into, oh, interesting. I gotta fix whatever typo happened over here. As we get into OSPF, which again is the purpose of this entire series. And keep in mind, as we start talking through this series, is that OSPF is a link state protocol, meaning it's going to have, every router is going to have full knowledge of the entire topology, and it's an IGP, meaning it's going to be tuned for speed and quick convergence. With that said, these are the key points I want to communicate in this lesson. In the next lesson, we're going to start diving deeper into OSPF itself, but that's the end of lesson 1. And so for now, I will go back to this guy, and I will see if you guys have any questions. Okay, cool. So that was the end of the first lesson. Let me know how that went. Any bugs, any typos, any things about the slides. Again, I want this to be the ultimate series for OSPF. So if there's anything that didn't communicate the key points on your screen in the best way possible, please let me know. If you thought it went great, mention that too in the chat room. And then once we've heard from a few folks, we can continue on with the next lesson. With that said, let me take a look to see if I missed any chats. Any questions? Cool. So Prelude mentioned BGP allows to influence incoming and outgoing traffic. Yes, BGP can do so much in that regards. I'm actually tempted to make a full BGP course, but we'll see if there's interest in that. I'm going to finish this OSPF course first. So Cordy asked the question, how significant is the RAM and CPU usage compared to distance vector? To be honest, in the modern day, it's completely insignificant difference. These protocols were created 20, 30 years ago, back when routers had 128K memory or 64K of memory, and the cost of RAM was very, very expensive, and the cost of bandwidth was very, very expensive. Nowadays, any router that's been built in the last, say, 10 years can handle millions and millions and millions of routes in both distance vector and OSPF routing protocols. So nowadays, the actual cost difference of RAM and CPU, that's not really what you're going to be using to make the decision. What you're going to be doing to make the decision between routing protocols, what features you want included. Good question, though. Udemy course. I do have some Udemy courses. If you go to classes.net, actually, and they're all also on my own website. If you go to pracnet.net/classes, you can see those. Cool, welcome, BB50. Glad you are enjoying the stuff. Awesome, you guys enjoyed it. Justin, you mentioned OSPF 2 versus 3. That might be something I'll circle back to later on. I don't know if you guys have seen the rest of my content. I'm very, very particular about what I communicate and when. I'm very, very meticulous about what concepts I introduce to essentially make it as easy as possible so that I'm not front loading too much information. So I'm very selective about what I present. Fosto asked, what's used more often in the field? OSPF for sure. OSPF is probably the most OSPF and ISIS are probably the most common routing protocols. EIGRP was huge when many networks were all Cisco networks, but nowadays most networks are kind of hybrid, different protocols, different vendors, and so you'll see OSPF and BGP used predominantly. Cool. Binary Dreamer asked about home routers and IGP. Since your home router is really one router and every device is connected to that one router, it's not even really using a routing protocol. It's just using default routing with static routing. Check out the Networking Fundamentals series to understand that a little bit more clearly. Cool. Sweet. So Vlada asked, why must OSPF areas be connected to area 0? We're actually covering that very shortly. So I'm going to delay on answering your question until we get to the slides. And I think that's it. Cool. And VJ, I just saw your question, and I'll speak to that when we get to those slides. Okay, awesome. So thank you for that feedback. Yes, QWERTY, you enable OSPF per interface. With that said, let's get into the next lesson. Okay, so we've moved past IGPs and EGPs and link state and distance vector. Now we're going to start talking specifically about the OSPF protocol. In this particular lesson, we're going to be looking at the different tables that are involved with OSPF and the packets that OSPF uses to do its thing. So OSPF uses 3 tables to do its job: a neighbor table, a topology table, and a routing table. I'm going to show you each of them shortly. In the definition of these, we're also going to be looking at 2 other very important OSPF terms. Those terms are the LSDB and the LSAs. Again, we'll talk about those shortly. And then finally, there are 5 packets that we want to talk about that OSPF uses to do all of its communication. And within those 5 packets is everything that OSPF does insofar as what routers will communicate with each other. So with that said, let's get right into talking about the OSPF tables. We're going to use this topology to talk through the idea of these tables. So the first of the tables that OSPF uses is what's called the neighbor table. And in the neighbor table, OSPF is going to have, every OSPF router is going to have a neighbor table. And inside that neighbor table, it's going to have knowledge of all the directly connected OSPF routers. Face in the way again. Let's fix this guy. Cool. So R5 is going to have a neighbor table, and inside R5's neighbor table, it's going to have, hey, I'm neighbors with R4. And then R4 is going to have a neighbor table, and R4 is going to have an entry for R5, R1, R2, and R3. And then R3 is going to have a neighbor table, and then in R3's neighbor table, it's going to have an entry for R4 and R2. Note that this is directly connected OSPF routers. So R3 is going to know about router 5 because it's a link state protocol in OSPF, so it knows about all the other routers. But R5 is not going to be a neighbor with R3. It's only directly connected OSPF routers. In this neighbor table, it's going to be a few pieces of information, but the most significant piece of information is going to be the state of the particular adjacency. Meaning, router 5 is going to have an entry that says, hey, for router 4, I am in full state, or for router 4, I am in, init state. And we're going to talk through the different states in a couple lessons, actually. So the main part about the neighbor tables is I'm going to know all my directly connected neighbors, and I'm going to know the state of the adjacency, the state of the relationship at the moment. So that's the main thing that's going to be in the neighbor table, which brings us to the topology table. The topology table is going to include everything that OSPF knows about. Earlier, I told you that router 3 is going to know about router 5, but not as a neighbor. Well, where that's going to be stored is in the topology table for OSPF. Now, OSPF calls its topology table the link state database, or the LSDB. It's simply what OSPF uses to refer to its topology table. The concept of a topology table is actually protocol agnostic. EIGRP has a topology table that stores all of everything EIGRP knows about. RIP has a topology table. ISIS has a topology table. They all call them something differently internal to the protocol. So the concept of a topology table is everything a particular routing protocol knows. And in the case of OSPF, the link state database is the name of the topology table. So again, when you see LSDB, think everything OSPF knows. Now, the entire table is the LSDB, but all the entries within the LSDB is referred to as an LSA. Let's actually use a permanent marker. Let's use a better pen. So an actual topology table, this is the topology table of a particular router, also referred to as an LSDB, but every single entry within the LSDB is referred to as an LSA. So each of these is a specific LSA. Each LSA is a piece of information that OSPF knows about, and we're going to be picking apart LSAs in great detail throughout this series. So for now, just know that an LSDB is the entire table, and an LSA is the individual entries within the table. And finally, the last table we're going to be talking about is the routing table. The R is a little cut off, but that's okay. The routing table is actually just the routers routing table itself. So it's not actually a function of OSPF. It's actually a function of the way routers work in general. So every router has a routing table. And what happens is OSPF is going to take its link state database and try and offer routes to the routing table for the router to use to actually route packets. So this, again, is a callback to the networking fundamentals lesson where we talked about every router has a routing table and it uses that to route different packets. So again, definitely check that out if any of that doesn't make sense. So again, the routing table isn't specifically an OSPF thing. It's just a router thing. And OSPF's topology table is known as a link state database. And every entry is an LSA. So that takes care of talking about the different tables that OSPF uses. Now let's talk about the packets. Now what we're going to do is talk about the packets in general here, but later on when we go through the adjacency state, we're going to look at the packets in more detail. With that said, there are 5 packets that we're going to be talking about, and we'll just start right at the top. This is the topology we'll use to talk about it, and we're going to start by talking about hello packets. So a hello packet is how routers will discover each other and start the neighbor adjacency. Hello packets are sent by every OSPF router to the IP address 224.0.0.5. This is a multicast address that's specifically reserved for all OSPF routers. The way it works is once I tell router 1 that it's doing OSPF, it's going to start listening for any incoming requests to 224.0.0.5. So if I want to send something to anybody that might be doing OSPF, I can send something to this multicast address. In the case of OSPF, hello packets are sent periodically to this address out all interfaces that OSPF is enabled for, and that's how router 1 will make contact with the other routers in this particular topology. So that's the purpose of the hello packets. It's how neighbors and OSPF peers will discover each other. The hello packets themselves include very significant pieces of information. They're going to be used to determine whether the adjacency is going to continue or not. And we're going to be unpacking that in a dedicated lesson where we look at the contents of the hello packet. That's the, and that information will be used to determine if an adjacency will form. So that's the main idea behind a hello packet, which brings us to a database descriptor packet, or a DBD. Now, let's get into it. So the main purpose of a DBD, or a database descriptor packet, is to send a summary of the LSAs in each router's link state database. So remember I told you that in a link state protocol, every router knows what every other router knows. So router 1 has a link state database full of a bunch of LSAs. But instead of initially sending the entire database to another router, what it's going to do is send a summary of the database to the other router. It's going to do this in a DBD packet. The idea there is router 2 might already know about some of the entries in router 1's link state database. And there's no sense for router 1 to send everything if router 2 doesn't need it. So what's going to happen is router 1 is going to say, hey, I know, I have these entries in my table. Let me know which ones of those you actually need. So that's the purpose of the DBD packets. It's also sometimes referred to as just a DD packet, but either way. It's sending a summary of the link state database. Now, I will mention there is another purpose for the database descriptor packet, and that's involved in what's called the master-slave election, but we'll unpack that when we get into the neighbor adjacency process later on. With that said, that's the hello and DBD packets. Next, we'll talk about the remaining 3 packets, starting with the LSR, or the link state request. An LSR packet is there to make a formal request for a complete LSA. So what happens is R1 will send a DBD packet with a summary of its link state database to R2. R2 will take a look at the database and be like, okay, I need entries A, B, and C. And router 2 will be like, and router 2 will send an LSR saying, hey, I need these specific entries. Router 1 will then send the full LSA with those specific entries in a link state update packet. And then router 2 will confirm receiving those link states in an LS acknowledgement, a link state acknowledgement packet, or LSAC. So make sure you see the reliability that OSPF is using here, right? an LSR is sent, and a router knows that the LSR is received because it'll then receive an LSU. And then a router knows that an LSU is received because it'll then receive an LSAC. So notice that there's intrinsic reliability to OSPF and how the packets are shared. We'll explore that more fully later. Now, if after the full synchronization of the database have occurred, router 1 learns of something new, router 1 is simply going to send a link state update to router 2 with a new piece of information, and then router 2 will respond with an LSAC. So these two packets will then be used going forward after the initial full synchronization of the database. So again, you can see that really these 5 packets handle all of the communication that OSPF requires, both the initial synchronization of the database and discovery of the neighbor, and ongoing updates to learning new things as they go. Cool. I think that that's it. Oh, and the last note is just a point of confusion. An LSAC is not the same thing as an LSA. Again, an LSA is simply an entry in a link state database. It's a piece of knowledge that OSPF knows about, whereas an LSAC is a type of packet that is sent in response to an LSU. With that said, here are the things that we talked about in this particular lesson. We unpacked the 3 OSPF tables that are used within OSPF, and then specifically that also let us define these 2 important terms, LSDBs and LSAs. And then finally, we also talked through the 5 different types of packets that exist in OSPF. In the next lesson, we're going to be looking at areas and types of routers. But for now, the main takeaways for this particular lesson is understanding all of the terms you see on your screen. And since we've come to a close of another lesson, we are now turning back to time for feedback. Let's go back to this screen. And again, that's lesson 2 of this series. How did it go? Was it enough to communicate the things that I meant to communicate in this lesson? That's the tables, LSDB, LSAs, and then OSPF packets. Any questions, mention them in the chat room. Any feedback, both positive or negative, mention them in the chat room. Let me know how that went. And then we'll go on to the next lesson after a moment of feedback. All right, let me see if I missed any questions. S Smooth asked if I'm on Udemy. Yes, all my classes, well, not all my classes. I have a couple classes on Udemy. They're pretty short, but you can reach all the other online courses that I offer at pracnet.net/classes, or my website, practicalnetworking.net. There's a little button for classes in the top right. Yep, areas we're going to get into next. Cool. Cool. And Ward asked the relationship between LSAs and LSUs. An LSA is simply an entry in the link state database. It's simply a piece of information that OSPF knows about, whereas an LSU is an actual packet that is used to request an LSA. So LSU is the packet that is used to, sorry, not request, LSR is request. LSU is the packet that is used to send a particular LSA. Correct. The Ultima also answered that question correctly as well. Yes, QWERTY, if an LSU is received by one router, it is going to be forwarded to the next router. At least if it's received insofar as a new update occurring. In the original synchronization, the LSDBs aren't automatically, well, actually, they actually are forwarded because everything's synchronized with everyone. But we'll unpack the process of learning new routes in more details later on. And cool, and some questions about the types of LSAs. We're going to pick types of LSAs out in great detail. Actually, so I used to teach CCNA and CCNP courses, and I have a way of teaching the LSAs, which tends to get people all the way there to really understanding the different purposes of the LSAs. In fact, we're going to do an exercise where I'm going to rebuild a network topology using only the OSPF database, just to show you the actual purpose of all of those LSDBs, because that's what the routers are going to be doing, right? The routers share all the LSAs, and they use that to rebuild the entire network topology. So if you guys are excited about that, like, subscribe, all that fun stuff, so you guys can see when that video drops. That won't be today. I'm actually trying to get somebody else to build the topology for me so that I don't know anything about the topology, right? I'm just going to ask for access to a terminal where I can run some show commands. And I'm only going to be running OSPF show commands, so I'm not going to do show CDP neighbor or anything like that. And I'll rebuild an entire OSPF topology using only the content of the link state database. So yes, so if there's any confusion about LSAs, trust me, in this series, you will have all of your questions answered when I get there. Cool. Chaitanya asked, what type of request is asked in an LSR? So in an LSR, you're asking for the full content of an LSA. The last lesson, I'm going to show it to you in Wireshark, actually, so you'll get to see that in more detail. Pedro asked about the transport protocol. OSPF uses its own transport protocol. It's protocol 89. We'll unpack that more. Won't be today, but it will be in future lessons. Cool. And then Vabav, how does a router identify its neighbor? I think we're actually going to be talking about that next. So we'll talk about that shortly. Sorry, we'll do areas next, and then 2 lessons from now, we'll talk about that. Okay, cool. Well, I think that covers the feedback, which now brings us to talking about areas. So let's go back to my teaching setup. Cool. Okay. Not muted. All right, sweet. So in this lesson, we're going to be talking about OSPF areas and the types of routers in OSPF. So critical to understanding OSPF is understanding the design of OSPF areas. And critical to understanding OSPF areas is understanding the types of routers you're going to come across in OSPF. So that's the lesson plan for today, is to unpack the idea of areas and the types of routers that exist in OSPF. Now, to talk through it, we're going to use this topology. So here we have a topology of 7 routers. And as I mentioned, OSPF is a link state protocol, which means every router knows about everything going on with all of the other routers. Notice that the way this topology is laid out, the only way for router 7 to get to routers 5 and 6, right, whatever networks might exist on router 5 and 6, is for the packets to go through router 3. In a link state protocol, everyone knows everything about everything. If something happens to a network over here, so say this link goes down or this link goes down, and router 3 needs to change the way it gets to these topologies. In a link state protocol, router 3 is then going to make updates that's going to get propagated to all the other routers in the topology. Even though, either way, these routers still only need to use router 3 to get to the networks below router 5 and router 6. So, yeah, cool. So because OSPF is a link state protocol, changes anywhere get propagated everywhere. One way that OSPF uses to contain that is by using what's called areas. The way it works is OSPF will designate certain routers, specifically certain router interfaces, in specific areas, and flooding of the LSDBs is contained to those areas. It's going to limit the propagation of LSAs to specific areas. In this particular topology, notice router 7, router 4, router 1, and 2, the only way for them to get to this blue square over here is to send the packets through router 3. And because of areas, if something happens with this particular link and router 3 now needs to go this direction to get to router 6 or router 5, since router 3 knows it doesn't affect anything outside of this blue area, it's not going to send the updates to the other routers in this topology. It knows that whatever they already knew is sufficient to get the packets to router 3, and it doesn't need to update with every little change that happens over here. So that's the benefit of areas, is it contains the propagation of LSAs to specific areas. OSPF areas allow for a 2-tier hierarchy. First, you have area 0 at the top. This is known as the backbone area. And then you have every other area. In this case, our blue area over here, we're calling it area 88. And our green area over here, we're calling it area 99. That's the two-tier hierarchy. You have everything, and then the top of the hierarchy is area 0. Now, someone asked about, can you have area 88 connect to area 99? The answer is no. All communication between the different areas has to go via the backbone. Again, it's only a two-tier hierarchy. The purpose of this is to assure loop-free topologies within the area design. If you could connect area 88 and area 99, you could introduce a routing loop that's going to cross from area to area to area. That's problematic because remember that the link state propagation is confined to the area. So the routers within an area aren't going to know there's a loop. That's why OSPF limits itself to a two-tier hierarchy, and everything has to go through the backbone. It creates what's known as a hub and spoke design, or a star topology if you prefer. Uh-oh, heads in the way. Really a good place. Let's go here. It creates a hub and spoke design, and the idea is everything is connected off of the hub, which is area 0. And if you had additional areas over here, they would all be connected into the hub into area 0, and then area 0 would handle funneling traffic between the different areas. So again, the purpose of the two-tier hierarchy and everything having to go through the backbone is loop prevention. Now, depending on where the routers exist within these different areas, determines what type of router those OSPF considers those routers to be. And there are 4 types of routers that we're going to talk about. Let's just get into it. The first is an internal router. An internal router is any router where all interfaces are in a single area. So router 1 is an internal area. Router 2 is an internal area. Notice all of those routers' interfaces are in area 0. Router 5 and 6 are also internal routers. All of their interfaces are in area 88. Router 7 is also an internal router. Then you have backbone routers. Backbone routers are routers who have at least one interface in area 0. So router 1 and router 2 are internal routers in area 0, obviously are backbone routers, but also router 3 and router 4. Because they have interfaces in area 0, they can also be considered backbone areas. Yes, QWERTY, the backbone is by designation area 0. That's the definition of a backbone, absolutely. Which then brings us to ABRs, or area border routers. ABRs are routers that sit on the boundary between areas. But remember that you can't have area 88 connected to area 99. So technically, the definition of a ABR is on the boundary of area 0 and something else. So one or more interface in area 0 and one or more interfaces in another area. So that's what an ABR is. The ABRs are pretty important in OSPF. They're the ones that actually contain the flooding of LSAs across areas. So if something happens in here, router 3 is going to have to make a decision about whether that something is important enough to send an update to all the other routers. If it's not, router 3 is essentially the termination for that particular piece of information. But if something happens that is important enough, obviously router 3 is going to have to send that into the other areas. So the role of containing the LSA flooding is based upon the router, the ABRs. Same thing with router 4 is also an ABR. So they're going to be responsible for summarizing routes. Yep, just mentioned that. Cool. Now, the last type of router that we're going to talk about, we're going to have to change our topology just slightly. We're going to have to have router 7 here redistribute routes from another routing protocol. As soon as router 7 is doing that, it is now referred to as an ASBR, or an Autonomous System Border Router. An ASBR is redistributing routes learned from some foreign mechanism into OSPF. In this example, router 7 is doing doing EIGRP with potentially other routers that exist over here. And whatever router 7 learned about in EIGRP, if it's redistributing that into the OSPF domain, router 7 is referred to as the ASBR for this OSPF domain. Now, to be clear, however, our example used EIGRP, but it doesn't have to be EIGRP specifically. It's really any other source of learning routes. So that includes other routing protocols, and that also includes static routes, or even directly connected routes. Any sort of redistribution that is happening makes router 7 an ASPR. There's a command that router 7 can use. So let's just say router 7 had a bunch of directly connected networks and therefore directly connected routes. Instead of adding each of those networks individually to OSPF, I can just tell router 7, hey, redistribute all of your directly connected routes into OSPF. And instantly that's going to make router 7 an ASPR. So anytime it's sending router updates from a different topology into OSPF, it is considered an ASPR. Yeah, and that's it. So the main things we wanted to talk about in this particular lesson is understanding the two-tier hierarchy of OSPF area design, where you have area 0 as the backbone, the top, the king, if you will, and then everything else being connected into the backbone. And then understand that the purpose of areas is to contain LSA propagation, and of course the 4 types of routers that we talked about. In the next lesson, we're going to be talking about hello packets, and then in the lesson after that, we're going to be talking about the neighbor adjacency process. The main takeaways for this lesson is what you see on your screen, and since that again is the close of another lesson, I am now going to turn it over to the chat for some feedback. Do you feel this set of lessons, an explanation, properly explain everything you see on your screen right now? If you have any questions or thoughts, both positive or negative, please mention them in the chat room. Let's go to this other screen over here. I'll now turn it over to you guys. Let me know what you guys think. Okay, so I'm not seeing any questions in the chat room or thoughts or feedback. I know there's quite a delay. Yes, correct. So basically OSPF is like a map that we know all the routes. It's a map beyond all the routes, but between areas, it actually acts as a distance vector protocol between areas, right? We only know everything up until the closest ABR, and after that is a bit of a mystery. We just know the networks, we don't know the actual routes happening on the other side. So correct, Ward. TTL will prevent a packet from being sent in a routing loop indefinitely. It'll automatically expire the packet, if you will. But in routing design, you don't want loops to exist if possible, because it's still the packet itself won't last forever, but it's still a lack of connectivity, right? So if we go back to this over here. So notice here we have a loop, right? Let's just say that there's a particular network that exists over here off of R5. Well, if R5 somehow thinks that network exists behind R6, and R6 thinks it exists behind R3, and R3 thinks it exists behind R5, what'll happen is a packet sent from, say, R2 to whatever network that was is going to hit R3 and then kind of do this forever until the packet expires. So the packet itself will expire because of the TTL, but we still won't have connectivity to the actual devices within that area. Cool. So that is a Ward's question. Fabe have asked, is it necessary for all areas must connect with area 0? Yes. If you want any communication to happen from one area to the next, it must go through area 0. Cool, Carlos, no worries. Virtual links are a way of you have to understand virtual links still connect a router that doesn't naturally have connectivity to area 0 into area 0. So it doesn't actually defy what we mentioned, that any communication between areas must still go through area 0. But we'll unpack virtual links later on in the course. For those of you who are just joining, no worries. I mean, I think within YouTube you can actually back up and catch the parts that you missed. You can actually do it on 2x speed as well, so it'll be quicker for you to catch up. Or catch us later, no worries. So Cordy An ASBR can be connected to other companies that are doing different routing domains. It can be connected to, routers within your own company network that is doing different routing protocols. There's many different uses for the ASBR. We're going to unpack that in more detail when we look at LSAs, and you'll see in more detail about the ASBR. You might be referring to the term autonomous system. If you've done any sort of reading on BGP, an AS number essentially identifies a particular BGP set of routers, and essentially every AS is a different company. But in OSPF's definition, an autonomous system is routing domains. So you could have a autonomous system that is all of your OSPF routers, and then another autonomous system that is your EIGRP routers or something else. Alfred, no, I'm not planning to cover MPLS in this series, just OSPF. Cool. So that takes care of the questions. And now we continue. So we've reached lesson 4. So thank you for your feedback and your questions. Again, please keep them coming. Again, the purpose of this is for this to be kind of like the end-all be-all series on OSPF. So any feedback, both positive or negative, any ways you feel this content can be improved upon, definitely let me know. With that said, let's get into the concept of hello packets. Let's pick that apart in more detail. Cool, so here we have a topology, 2 routers directly connected to each other and some IP addresses configured in that particular link. As we mentioned before, hello packets are sent from one OSPF router to another. Real quick to speak to Mike's question, you can do that, but you'd essentially have OSPF routes redistributed into another OSPF topology. So I told you an ASBR can redistribute routes from a foreign routing protocol. That also includes routes from one OSPF domain to another OSPF domain. So within each of the domains, you only have one area 0. By rule, you can only have one area 0. But in the case of company mergers, there's games you can play to make it appear like they're 2 different OSPF domains. Cool. So, sorry, just a solid question, and I want to speak to it before we continue. So hello packets are sent from one router to another to discover each other's presence. This is how routers discover other routers and become neighbors with those routers. These hello packets are sent periodically to this address. We mentioned that earlier. That's the multicast address for all OSPF routers. If you think about it, when router 2 initially sent out this packet, it doesn't know that router 1 exists. It's just sending it out. It's just saying, hey, hello, are you out there? Hello, are you out there? Hello, are you out there? Once router 1 is configured with OSPF, it'll then receive those packets and then respond with a hello of its own. Typically, the hello packets are sent out every 10 seconds. That's governed by what's called the hello interval. You can configure that if you want, but that's an idea of how often you should see those. There are some types of network that don't support sending multicast packets. These are known as non-broadcast networks, but we'll talk more about the different network types in OSPF later on. But in the case of networks that don't support multicast, since you can't send something to a multicast address on those networks, what you have to do is configure the peer IP address manually, and then your and then your hello packets will be sent directly to the peer IP that you configure. So in those cases, hello packets are sent unicast, but most of the time you're on a type of network that does support multicast, and your hello packets are going to be sent via multicast. But there are times when that's not the case. Inside this hello packet is a bunch of useful information that the routers are going to use to determine if they actually want to become friends, right? And the purpose of this lesson is to unpack all the information inside a hello packet. So with that said, let's now look into the content of a hello packet to really pick apart what is inside these hello packets. So the first thing we're going to look at is the router ID. So the first field inside a hello packet is the router ID, and the router ID is the identity of each router. In the case of router 2's router ID is what looks like an IP address of 2.2.2.2. Now the actual router ID field is a 32-bit field, so it can be any combination of 32 ones and zeros. And it's typically represented by something that looks like an IP address. but it isn't actually an IP address, right? The IP address 2.2.2.2 doesn't actually exist on router 2, or doesn't have to actually exist on router 2. It's simply the identity of router 2. The next thing inside a hello packet is the hello interval. We told you earlier that the hello interval is the frequency of those periodic hellos. Most of the time you'll see 10 seconds. On certain types of networks it defaults to 30 seconds, but we'll unpack that in more detail. Either way, when router 2 is sending out a hello packet, it's also saying, by the way, I'm going to be sending these every 10 seconds. The other thing that's included inside these hello packets is what's called the dead interval, or the dead timer. What this is a duration that router 2 is claiming to remember what else it learns about from other routers. So what happens is these hello packets end up becoming keep alives or health checks. So if I'm router 1 and I've joined a neighbor adjacency with router 2, I'm going to expect router 2 to send a hello every 10 seconds, right? And if I don't hear anything from router 2 after 40 seconds, the dead interval, I'm going to forget that router 2 existed. So that's the dead interval. Typically, this is set to 4 times the hello interval. The idea there is I can miss at least 3 hellos before I forget that you existed, and I forget everything that you've ever I've ever learned from you, right? So that's the dead interval. And again, both of those things are included in the hello packets that are being sent. The next thing we're going to talk about is the neighbors field. Now, this is actually a very important field, and we're going to unpack this in more detail later on. But the neighbors field is essentially a field that says, here are the other neighbors I see on this link. Now, at this point in time, router 2 is simply sending out these periodic hellos. It still hasn't heard anything from router 1. So at this point in time, router 2 doesn't know that any other router exists. All router 2 knows, therefore, router 2's hello packet includes a neighbor field that says empty. Router 2 doesn't currently see anybody else on this link. Later on, once router 1 starts sending hello packets, then router 2 will add to its neighbors field that it now sees router 1. This is how router 1 is going to know that router 2 sees it, because it's going to see itself in its peers neighbors section of the hello packet. And I'll show that to you later on. Like I just mentioned, this is how these routers are going to validate two-way reachability. And again, this is a very important field, and we're going to unpack it in more detail as we go. Cool. Next, inside the hello packet is an area ID. We talked about the concept of areas in the last section. Router 2 is going to include in its hello packet that it thinks it's in area 0. And it's also going to include any sort of authentication data. So with routing protocols, you can add a password to your routing protocol and say, hey, I only want to become neighbors with everybody who has the exact same password. That authentication data is included in the hello packets in a field known as authentication data. In the case of router 2, we're not doing any sort of password-based peering. Cool. And finally, the last thing is they're going to include the subnet mask of the link in the hello packet. So in this particular case, R2 thinks that this network is a /20 forward network. Cool. So those are the first 7 things that we wanted to talk through inside a hello packet. There's 2 other groups of items that we want to talk about as well. But for that, I'm going to use another slide. So to start, make sure you understand these 7 things. And with that, let's talk about one more thing inside the hello packet. Now, for both of these next 2 things that we talk about, we're going to unpack them in more detail later on in this course. But for now, I just want to give you kind of a definition, a high-level definition of what each of these things are. The first thing we're going to talk about is the area type. And there are 3 options here: normal, stub, and NSSA. And again, we'll explore this in more detail later on. But for now, I just want to give you a definition of what each of these are. And so for that, I'm going to use the area topology that we used before. So a normal area is essentially the default type of area that you see in OSPF. These other 2 are ways to optimize the areas even further. And so let's talk about it. The first is a stub area. A stub area is an area that only has one way out of that particular area. Notice area 88 over here actually fits that definition. The way it works is normally area 88 is going to, so let's just say area 0 had 100 routes and area 99 had another 100 routes. In a normal area, if area 88 is configured as a normal area, it's going to have all 200 of those routes propagated in area 88. But as an optimization, what you can do is tell area 88 that it is a stub route. And what that'll do is it'll prevent the flooding of routes from a foreign autonomous system into area 88, and it'll replace those with a default gateway, with a default route. The idea there is if there's thousands and thousands and thousands and thousands of routes in this EIGRP topology, there really isn't a sense of having all of those 1,000 routes propagated in area 99, area 0, and area 88, because either way, area 88 only has one way out of that network. So what you can do is tell area 88 that it is a stub network, and that's going to limit the propagation of these foreign routes and be replaced with just a default route pointing to router 3. So it's an optimization that you can use. The last one, the other one we're going to talk about is the NSSA, which stands for Not So Stubby Area. This is essentially the same thing, but it's an area that only has one way out, but also allows for an ASPR, also allows for redistribution. Both of these things, stub areas and NSSA, are things we're going to look at in more detail later on in the series. For now, I just want to mention that these exist, and they exist for the sake of optimizing the routing tables within specific areas, and they are included in the hello packets that are sent from router to router. So again, the main idea here is just understand that these exist, and they are optimizations to the routing table. Cool. And then the other three things we want to talk about are these three: the DR, the BDR, and the priority. To talk about those, we're going to extend our network a little bit. We're going to add another network over here down on router 2. And on this network, router 2 is going to be neighbors with router 3, router 4, and router 5. Now, yes, Mike, that's one of the ways that optimization works. So I'm reading Veba's question. Does it have interface network details also? I'm not sure I fully follow your question, so feel free to elaborate on that. And correct, Eugene, for non-broadcast, it does default to 30 seconds on the hello timer and 120 for the dead timer. Cool. And yeah, I'm sure once you get it wrong on the practice exam, right, that'll help you get it right for the actual exam. So congrats. Okay. So again, these three things, we're going to have a separate lesson where we dedicate to talking about multi-axis segments and how propagation works and the roles of these three things. So for now, again, I just want to stay high level and give you a simple definition of why they exist and why we need them. So let's go through an example. So router 1, router 2 are neighbors, and then router 2 is neighbors with all of these routers, and all of these routers are also neighbors with each other. With normal propagation, what happens is if router 1 learns something new, router 1 is instantly going to be like, oh my gosh, cool, I just learned something new. I have to tell my friends about it. And router 1 is going to forward that to router 2. And then router 2 is going to be like, whoa, cool, I just learned something new. I have to tell my friends. And then router 2 is going to forward that to router 3, router 4, and router 5. And then router 3, having just learned something new, is going to be like, oh, cool, I just learned something new. I have to tell all of my friends. And then router 3 is going to forward that to router 2, router 4, and router 5. And then router 4, having just learned something new, is also going to forward it to router 2, router 3, and router 5. Notice the same update that initially was triggered by router 1 got sent to router 2, and because all of these are routers with each other, they're duplicating LSAs to each other and updates to each other redundantly. That's problematic because you're wasting processing time on the routers and wasting time bandwidth that is unnecessary. To do that, rather, the way OSPF compensates for that is on any link that is a multi-axis link. Notice over here we have multiple neighbors on that particular link. What happens is a DR, a designated router, is elected, and that designated router is the central point for all updates on that particular link. So if we go through that same topology, use the same example rather, using router 3 as our example designated router, what happens is when router 1 learns something new, it's going to update router 2. when router 2 learns something new, instead of sending that update to everybody on the multi-access link, it's just going to send the update to the designated router. The designated router is then going to be responsible for forwarding that to the other neighbors on that particular link. There's also a backup designated router that is elected, and this guy is only going to do things if this guy fails. And what goes into the election of the designated router and the BDR is what's known as the router priority. All three of these fields exist in a hello packet. So when router 2 is sending out hello packets, it's sending out, hey, this is the designated router IP address that I know about. This is the backup designated router IP address that I know about. And this is my priority. Router 2 is sending out its own priority. In OSPF, higher priority is better. So it's possible because of router 3 and router 4's election status. Maybe router 3 had a priority of 50, and router 4 had a priority of 25, and router 5 and router 2 had the default priorities of 1. That's what made router 3 the designated router. Either way, this concept of the designated router is how redundant updates are limited or prevented, if you will. Because what happens is whenever router 2 has something new, it just tells the DR, and then the DR passes it on to everybody else. And so you don't have this everybody sending updates to everybody else situation. Cool. Now, the last thing I want to mention about this is understand when we say multi-access, I don't actually mean there are multiple routers on the link. What I mean is that the link has the potential for multiple access. Let's take a look at router 1 and router 2 over here. If router 1 and router 2 are connected via Ethernet, right, Ethernet cables, that means there might be a hub on this link. There might be a switch on this link. There's no way for router 1 and router 2 to know that. All they know is they have IP connectivity to another router using the IP addresses 10.122 and 10.121. So if there might be a hub over here, it might be possible that at some point in the future, another router will be connected to that hub. Since there is the potential for multiple access on that particular link, this also would be considered a multi-access link, even though you and I can see the topology and see that there are only 2 routers on this particular link. Since this is plugged in via Ethernet, which is technology that supports multiple access, there is the potential for multiple routers, and therefore a DR and BDR election will happen on this link. One of these would become the DR, and then the other one would become the backup designated router, depending upon which interface, the priority numbers for each of those interfaces. So understand, when I say on multi-access, I mean the potential for multiple access. So technologies, connectivity technologies that don't include the possibility for multiple access, things like serial or certain types of tunnels, where there's only 2 people, right? There's only one side of the tunnel and the other side of the tunnel, and it's impossible for somebody else to exist in the middle. Those are links that don't support multiple access, and on those links, you don't need to do a DR-BDR election. So again, on multi-access links, you're going to see a DR-BDR election, and those things are also included in the hello packets that are sent from router to router. So here are the 7 things we talked about before, and then here are the new 4 things that we talked about just now. Each of these 4 we're going to be unpacking in more detail later on in the series. So if right now you don't understand the full implication of each of them, that's totally cool. Just understand a high-level definition. Area types are a way of optimizing the routes within an area, and BDRs, DRs, and the priority number are a way of electing a designated router on a multi-access segment to reduce redundant router advertisements, or link state advertisements. So the main takeaway of this lesson is understanding all of the content inside of a hello packet. And one more thing. Remember I told you that the information inside a hello packet is what's going to determine whether router 2 and router 1 are going to become friends, they're going to become neighbors with each other. Which means there are certain pieces of information in the hello packet which must match for router 1 and router 2 to actually become friends with each other. Let me just get rid of this for now because it's in the way. Become friends with each other. Those pieces of information are these six right here. They have to agree upon their hello and dead intervals. If you think about it, if router 2 rather is sending out a hello and dead interval of 10 seconds and 40 seconds, but router 1 prefers that to be at 2 seconds and 6 seconds, they're going to have a hard time maintaining a router adjacency. Because every 6 seconds, router 1 is going to forget about router 2, and router 2 is only sending these every 10 seconds. So if these things don't match, router 1 and router 2 will not become neighbors with each other. The area ID, if router 2 thinks that this is area 0 and router 1 thinks that this is area 99, then they're going to have a problem agreeing upon what route should be shared with one another. So they have to agree, they have to match on which area they think that particular link is in. Obviously, the purpose of authentication data is to do password restricted neighborship. So if they disagree upon what the password is or whether there is authentication on this link, they're not going to become neighbors. They have to agree on the network mask on this link. If router 2 thinks that this is a /24 and router 1 thinks this is a /23, if they can't even agree upon what size network is on the link between them, they definitely aren't going to agree upon the rest of the networks in the topology. So the network mask has to match. And finally, the area type also has to match. If router 2 thinks this is a stub area, router 1 must also think this is a stub area, or they're not going to become friends with another. Cool. So that actually wraps up what I wanted to communicate in this particular lesson. And again, I'll turn it over to questions and feedback. Do you feel this set of slides and lecture was enough to properly communicate all the contents of the hello packets and which are needed to match for a neighbor adjacency to form? And again, we're going to unpack these in more detail in a few lessons, some dedicated lessons. But for now, I just want to make sure that you guys have a good rundown on all of this right here. So let me go back to this guy, turn on my camera again. Cool, there it is. Sweet. All right, so let me turn it over to you guys while I'm sipping some coffee and seeing if there's any feedback or questions or concerns about anything we just talked about insofar as hello packets. Awesome, cool. Thank you, Ward. Thank you. Glad you guys enjoyed it. So go back to the question about authentication data. So that's smooth. You asked about authentication data. So yes, ideally only the administrators are configuring routers, but you have to consider what else is connected to the network. And that's your users' computers and your users' phones and PCs and laptops. And if one of them decides they want to be malicious and join your OSPF domain, they can also start sending hello packets out into the network to try and join your OSPF domain. If they do so, that's bad for two reasons. One, remember this is linked state, so they know any OSPF neighbor knows everything about the entire network. So they'll be able to they'll be able to draw out your entire topology just from entering that OSPF neighborship. And two, even worse, even more malicious, they can start injecting routes, right? What if they said that the DNS server you're trying to reach to is actually their DNS server? Now they can control all of your web traffic. So often in enterprises where users are connecting into the network, which is most networks, you'd want to set up authentication so that you're only doing OSPF adjacency with trusted sources, not someone doing something malicious. Cool. And Eugene asked about the process ID number. Yes, in OSPF it can be. It doesn't have to match. In the IGRP it does. But we'll look at the configuration of OSPF shortly, and we'll talk more about that. Cool. And I think that covers all of the questions. Okay, so we continue. this guy back on. Let's see if we can. Okay. So let's continue. All right. In the last lesson, we talked through the OSPF packets. We talked through all the information that exists inside the OSPF packets. Inside the OSPF hello packets. And then in the lesson prior to that, we talked through a basic definition of the purpose of the rest of the packets in OSPF, the DBDs, the LSUs, the LSRs, and the LSAC. In this lesson, we're going to show you exactly what sequence of events happens with these packets for an adjacency to form between router 1 and router 2. So again, if any of that is unclear, feel free to get back up in this live stream, or if you're watching this after the fact, back up in the video and make sure you understand the basic premise of each of these types of packets. When we talk about the hello packets, we talked through all the different things that exist within the hello packets. We also talked about the faces in the way. Yeah, that'll work. We also talked about the things which must match in the hello packet for a neighborship to form. For the sake of our example, R1 and R2, everything checks out, everything matches, and we're going to step through the adjacency process. Now, I do want to highlight the definition of these two, the router ID and the neighbors field. Initially, in router 2's hello packets, router 2 is going to have a router ID of itself. And for the sake of our example, the router IDs are going to be 11111 for router 1 and 2222 for router 2. Moreover, inside those hello packets is going to be a neighbors field that's going to include what it sees if there's another router on the link. Make sure you understand that as we step through. I feel like my slides skipped something. This is the full adjacency process. Notice it starts with down, ends with full, but we're going to pick it apart in detail, so here we go. So when you first configure OSPF on a router, the neighbor state of that OSPF router is down. Right? So this is the initial state when OSPF is first configured. So from the perspective of R1, it's currently in the down state. Now, technically, in the down state, router 1 is periodically sending out the hello packets to try and discover other neighbors. It's doing it to the multicast address that we mentioned before. Now, technically, the down state is kind of a non-state, right? So remember, we told you that inside the neighbor table is a particular neighbor. So inside R1's neighbor table, this is R1's neighbor table. I'm writing with my finger, so sorry if it's gonna be very not neat. But in router 1's neighbor table, it's going to have an entry for a particular neighbor and the state that it's in. That neighbor entry, though, is going to be based upon the neighbor's router ID. The issue, router ID or IP address. The issue is, since router 2 hasn't sent anything at this point in time, router 1 has nothing it can really add over here. So down doesn't really exist, because since there's no entry over here, it doesn't actually know that anything is down. It doesn't know that any other router even exists on that link for it to be down. So technically, down is the initial state when OSPF is first configured, but do understand it's sort of a non-state because there is no entry that can exist in the neighbor table. So if you don't see anything in the neighbor table, then the current state of a particular neighbor relationship is down. In any case, in the down state, when router 1 is sending out its hellos, the neighbors field of the hello packet is going to be empty. Again, since we haven't heard anything from router 2 at this point, router 1 is simply sending out these hellos periodically with an empty neighbors field. Now, there's another state, the attempt state. You actually only see this on what's called non-broadcast multi-access links. Remember I told you on non-broadcast links, we can't send something to a multicast address. In those cases, you have to manually configure the neighbor, and in those cases, the hello packets are sent unicast, meaning to the IP address that you have manually configured. When that happens, you will see an entry in the neighbor table that says, hey, for this particular neighbor, we are currently attempting to create a neighbor adjacency. So again, you'll only see the attempt state on NBMA links, on non-broadcast multi-access links. Most of the time, however, you can send to multicast, and you're going to go from down to the next state that we're going to talk about. So in the down state, router 1 is periodically sending out these neighbor hellos, right? It's just like, hey, are you out there? Hey, are you out there? Hey, are you out there? In each case, the neighbors field is going to be empty until we hear something from router 2. So router 1 will do this indefinitely until router 2 gets configured. If router 2 at this point is configured with OSPF, it again starts in down just like router 1 does, and then router 2 starts sending out hello packets. In the first packet that router 2 sends out, the neighbors field is going to be empty because again, you'll notice it was configured after this guy, so that guy doesn't technically count. Let's use a different color. So this hello packet will be the first hello packet that router 1 notices. And when router 1 gets it, all future hello packets sent by router 1 are going to now include information about router 2. In fact, as soon as router 1 receives a hello packet, it's going to instantly go into the init state, or the initialization state. In the init state, it means that router 1 has finally received a hello packet from a neighbor, and now any hello packet that router 1 sends is going to include in the neighbor section the router ID of the neighbor that it heard about. Upon receiving that hello packet, router 2 is then going to go into the two-way state. The two-way, and in the neighbors field of that hello packet, router 2 saw itself. Since it saw itself, it knows there is two-way reachability on this link. That's the two-way state. Oops. That's the two-way state. Router 2 knows that router 1 received its hello packet, and router 2 obviously just received router 1's packet, so we know there is two-way reachability on this particular link. After router 2 receives this packet, receives the hello packet, its hellos can now start including the router ID of its neighbor, router 1. Cool. And then when router 1 sees its own router ID in the incoming hello packet, it too then goes to the two-way state. So the first states that we were talking about, so down, and then the attempt state, of course, but then down, init, and two-way are a pretty significant starting point, if you will, for the neighbor adjacency process. Notice router 1 went from down to init to two-way, and notice router 2 went from down to two-way. That's perfectly normal because two-way happens when you see yourself in the OSPF hellos of your neighbor, and the first thing that router 2 did is it saw itself, therefore was able to go directly to two-way state. Whereas router 1 received a hello packet with an empty neighbors field, so therefore went to init state, and then once it saw itself in the neighbors hello packets neighbors field, it then goes to the two-way state. Those are the first three states that we are talking about. Well, four if you talk about attempt as well. Cool. In the two-way state, the neighbors are going to decide if they're going to continue with the adjacency. Remember, we went through a bunch of other pieces of information that exist in the hello packets. They're going to use that information to decide if they're going to continue with a neighbor relationship. If they are, they will both continue. So at this point, they are both in the two-way state, and they'll now both continue by going into the X start state. That's exchange start. In the X start state, both of the peers are going to be sending DBD packets to each other. database descriptor packets to each other. Now, the initial purpose of these DBD packets is to do the master-slave election. What happens is one of these routers will be elected as the master, and then the other one will be the slave, and the communication flow from that point forward will always go master says something, slave response. Master says something, slave response, all right? This is how they're going to do reliable exchanges of their link state databases. So the master-slave election initially starts out, both of them send out a DBD thinking that they are the master. Inside that field, rather based upon the hello packets, you could say, the master will be elected. So the higher router ID becomes the master. In our example, that's router 2. Router 2 has a router ID of 2222. Router 1 is all ones. This is a numerically higher router ID. Therefore, router 2 becomes the master. And the next thing that happens is the slave is going to send a confirming DBD to confirm that it indeed is the slave of this relationship. So initially, they both send out a DBD thinking that they are the master. They compare each other's router IDs. And then the slave sends out a confirming DBD saying, no, I am indeed the slave. The slave goes to exchange as soon as it sends the confirming DBD. And then the master goes into exchange as soon as it receives the confirming database descriptor packet. So at this point, the master-slave process is complete, and now they can actually start exchanging their link state databases. Remember I told you the main purpose of the DBD packet was to send the summary of the link state databases. Well, what happens is when the master-slave election is complete, the slave then also sends a summary of its link state database. And then the master then sends a summary of its link state database. And from there, the slave confirms, and then from there, they're going to look at each other's link state databases to figure out, to figure out what, to figure out what entries they need from each other. Now, remember I told you that the way this reliable DBD exchange happens is the master says something, slave responses. Master says something, slave responses. The initial DBD sent from the slave before the slave knew it was the slave doesn't count. So if we ignore this guy right here, you'll see master says something, slave response. Master says something, slave response. Sometimes the LSDBs are really big. Think of routers with thousands and thousands of networks. In those cases, more of these DBDs will need to be sent to include the complete LSDB summary. But in all cases, it's always going to be based upon this reliable exchange of DBDs of master says something, slave response, master says something, slave response, and so on. I'm going to show you a Wireshark capture, and you'll actually see this live. But that's how that's going to work. In any case, once each peer has each other's link state database, they are currently in the loading state. In the loading state, they know the LSAs that each of them have, and they start figuring out which ones that they need. For all of the LSAs that they need, they'll go through an LSR, LSU, or LSAC process. What will happen is one of them, in this case router 1, will send out a link state request. This will prompt router 2 to respond with a link state update, and then finally router 1 will confirm with the link state acknowledgement. Inside the LSR is a request for a particular set of LSAs. It's going to say, hey, send me LSA X, LSA Y, and LSA Z. Inside the LSU are the actual LSAs themselves. Again, the LSAs is the entry in the link state database. Let's get back on. Yeah. And we'll go to this corner. And then inside, of course, the LSAC. Inside the LSAC is confirmation that a particular set of LSAs was received. Again, notice the reliability. LSR, we know the LSR was received because we got the LSA. We know the LSA was received because we got the LSAC. I should say the LSU was received because we got the LSAC. As soon as As soon as router 1, in this case, sends the acknowledgement for the LSA, so as soon as router 1 received the LSAs it was looking for, router 1 will go into full state. In full state, the LSDBs are synchronized. Of course, we want to do this in both directions. So at this point, router 2 is going to send its link state request asking for specific LSAs. Router 1 is going to respond with the LSUs that were requested. Router 1 will send a confirmation. And then, router 2 will send the confirmation, and then router 2 will go into full state. This is now the end of the neighbor adjacency process, and both peers have synchronized their link state databases. Remember, OSPF is a link state protocol, so both peers are going to have identical link state databases, and we just step through the process that is used to complete the adjacency and synchronize those topology tables, those LSDBs. So again, the full process we step through looked like this, and that is actually the main key point that I wanted to communicate in this particular lesson. In the next lesson, we're actually going to do a demonstration where I configure 2 routers as OSPF peers, and we're essentially going to walk back through everything we've learned so far and prove it to you visually using GNS3. The main takeaway for this lesson is understanding all the different stages of the OSPF adjacency sequence. And again, I'll turn it over to you all. If there's any questions, comments, feedbacks, did it go well? Do you feel this set of content has properly explained the full actual OSPF adjacency? So let me go back to this over here. Okay, cool. So let me know in the chat, did it go well? Did it go bad? Do you feel like you got enough information? You didn't get enough information? Mention something in the chat. If you feel like it was sufficient, mention that in the chat. And then once I hear from a few of you, we will continue with the actual configuration demonstration. Cool. Thanks, Eugene. Glad you enjoyed it. Thank you, Bellotta. Glad you enjoyed it. We're actually look at the process ID next. Acquisata. I don't know if you said your name right, but we're going to look at that next. So you'll kind of see the implications of that. Yeah, for sure. And awesome, Ward. Glad you enjoyed it. Mike, you too. Glad you enjoyed it. Cool. Cool. Doesn't look like there are any questions. So we can continue. So what we have next is going to be a live configuration demonstration of OSPF. And the point is going to be to prove all the various things we talked about today. I'm going to briefly introduce a bunch of OSPF commands, but all of them we'll look at in more detail later on. But the point for now is just to kind of land the plane a lot of these concepts and sort of prove to you the different concepts that we've talked about. With that said, let's get into the demonstration. Okay, so the 6th lesson in the series is really just a demonstration of everything we've learned in lessons 1 through 5. And again, the purpose of this is so that you're not just taking my word for it. You actually believe these things for yourself and believe them and prove them to yourself of how they work. What we are going to be doing is really just stepping through a demonstration where we explore everything we've talked about so far. So as you can see, like this lesson, this slide actually isn't even complete, but this is kind of a quick rundown and everything we've talked about so far. So let's actually pull up the cool. So I'm going to take all of this and I'm going to throw it into Notepad, and we'll use that to kind of make sure we talked about everything we mean to. A little bit smaller. Cool. So I currently have this topology built. Oh, my face. Cool. So I currently have this topology built out in GNS3. In this topology, we have two routers. Router 2 over here and router 1. They're connected via a serial link. I chose to use serial because serial is a point-to-point technology, so we're not going to have to deal with the BDR and DR election. Again, we'll talk about that in more detail later on. Ward, I just read your comment. That's a good question. Rather, that's a good suggestion. Definitely consider that as a quiz. Cool. In any case, in this topology, both the routers are in the same area, in this case, area 0. We're keeping it very, very simple. And then there's 3 networks that are connected to router 1 as loopback interfaces on router 1. I'll show that to you shortly. That's the 10.170/24 network, 10.1.8.0, and 10.1.9.0. And then router 2 also has its own set of networks that it's going to share. At some point, these networks will be known about on router 1, and then router 1 will know it the other way as well. So with that said, let's fire up these devices and get right into it. All right, so let's make this a little bit bigger as well. That's 16, so this is router 1. And then we'll open up router 2 over here. Let's change the colors slightly different. Cool. There's router 2. So we're going to start off by kind of just looking around to give you an idea of the topology. At the moment, nothing OSPF related is configured. So currently we're on router 2. That's this router down in here. And if I do a show IP int status, show IP int, brief, you'll see that I currently have the serial link configured as the link between the devices. Most of the time, the way I configure my IP addresses is start at 10 dot because why not? The second octet is going to be the area. In this case, we're area 0. The third octet represents the 2 routers on this link. In this case, this is the link between router 1 and router 2. And then finally, the router number is the interface, the 4th octet. This will be useful as our topologies get more and more complicated, because we'll be able to quickly see where a particular network exists. Notice here I've got 3 loopback interfaces configured, representing these 3 networks over here on the other side of router 2. Now, most of the time, instead of using this command, I'll use this command, show IP int brief exclude UNA. What that's going to do is it's going to exclude any line that has the letters UNA, which is going to filter for this word. And the idea there is it's going to show me only the parts of this command that are useful to me, what's configured. If we did the exact same thing on router 1 over here, I'm going to make that bigger because I have a pet peeve of these commands showing up on 2 lines. Exact same thing on router 1. You'll see that router 1 also has the serial link configured and has these 3 loopback interfaces configured. If I do show CDP neighbor, the routers see each other. This is router 1 seeing router 2. And if I ping the other router, ping 10.2.2, you'll see that they currently have connectivity. So everything insofar as before OSPF has already been configured. Maybe I'll put this up top. Okay. So everything insofar as the routers has already been configured. All we're going to be doing in this lesson demonstration is showing you the OSPF portion of everything. Okay, so let's get into it. So to start, I want to show you some show commands for OSPF commands. Right now, no OSPF has been configured, so most of these will show up as empty, but I want to show you essentially the before and after from our configuration in our demonstration. So the first thing I'm going to do is show you the command show IP protocols. This is a command you're going to use to show you whether OSPF is whether any routing protocol has been configured on your router. Notice the output to this command doesn't say anything about OSPF. You're going to see that change shortly as we configure the first part of OSPF. The other thing I want to show you is show IP OSPF interface and show IP OSPF brief. Notice both of those say nothing at the moment because at the moment router 1 has no interfaces participating in OSPF. You'll see both of these change shortly. To configure OSPF, the first thing you want to do is type router OSPF. You know, that's actually right at the bottom of the screen. Can you guys see that? Is the YouTube like progress bar or whatever in the way of that? Maybe we make this a little bit higher. I think that'll be better for you guys. Yeah. So to configure OSPF, you would type router, then OSPF, and then you have to put in a process ID number. Now in OSPF, neighboring routers don't have to have matching process ID numbers. It doesn't actually matter. You'll see a lot of people will use an example of router OSPF 1 or whatever the case. I personally like to use router OSPF 110. Now hopefully some of you can guess as to why I like to use OSPF 110. The idea is to create a link between OSPF and the number 110. So pop quiz, answer either in the comments or in the chat room. Why do you think I like to use 110 as a process ID number when configuring OSPF? Yeah, you guys called it out right away. Absolutely, the AD. I've always kind of gotten the habit of like, I'll use 90 for EIGRP, 120 for RIP, and 110 for OSPF. And the purpose is simply to, again, draw an association in my mind for OSPF and 110. If you guys are all studying CCNA, CCNP, I would highly recommend doing the same just to further reinforce the link between 110 and OSPF. In any case, router OSPF 110, and then I'm going to hit enter. From here, if I do show IP protocols, you're going to see something new has appeared. Remember before, we had nothing in here in this command about OSPF, so this is where I typed in the command up in here. But now we have a section indicating some OSPF stuff has been configured. Now there's a lot of stuff here that we don't really need to know about too much. Notice it picked a router ID for itself. And notice in here, number of areas this router is in, 0, because it's not in actually any areas at the moment because we haven't added any interfaces. Down in here, routing for networks, you'll see that populate in a minute as we add some networks to this OSPF process. Now the first thing I want to do is change this router ID. Now to change the router ID, router OSPF 110, I'm going to use the command router ID and then a number. In fact, let's see. It's asking for it in IP address format. But really, any 32, this is just a 32-bit field. If I, oops, sorry, I paste, this was, I hit the right click and it automatically painted that. This is the command that I typed. If I come back in here and go to show IP protocols, you'll see that now my router ID is something a little bit more sensible. Then I'm going to turn on OSPF on the link between the two routers. So we'll take a look at the router IP addresses. And this is the interface that I want to turn OSPF on. I'll come back and do the packet capture. You'll see this in a minute. So to turn on OSPF on a particular interface, I'm going to go into the OSPF process, and then I'm going to use the network command. The network command is going to be trying to match a particular interface IP address. And what it does is whatever interface IP address that I match, OSPF will start advertising the entire network associated with that interface. And the easiest way to do this is to just use the interface IP address directly. And now you'll see OSPF is going to ask for a wildcard mask. Now, I'm not going to unpack the idea of wildcard masks in this lesson. I did create another lesson on YouTube about wildcard masks. I think if you Google for it, or at least search for my channel, you'll see it. Definitely check that out if you're unsure about what wildcard mask or the implication. In this case, I'm going to use a /32 wildcard mask to say just match exactly this IP address. Now, if I hit question mark, you'll see it's asking me for the word area. And now if I hit question mark, you'll see it's asking me for an area ID. The area ID is a 32-bit field. You can actually put the area ID in IP address form. Some people do, some people don't. Most of the time, people just put it as a number. And I could put any number I wanted to be the area. For the case of our example, we're going to be using area 0. So I'm going to say this is an area 0. And here I hit enter. As soon as I've done that, I've enabled OSPF on that particular interface. If I do show IP protocols, you'll see over here, I'm currently routing for a particular network. I have something in my in the networks portion of the show IP protocols command. If I scroll back up to where I did this before, just to show you, oops, this is where I did it before. Notice I had nothing until I added the network command. So that's where we're at so far. And of course, now if I do show IP OSPF interface brief, we'll see that I currently have an interface participating in OSPF. So this is how I can confirm that I am currently running OSPF on serial 1.0, which is the interface between router 1 and router 2. If I looked at this command without the brief option, I can just hit enter. That'll give me a lot of information about the interface. We don't have to go through all of it. This is more information than we need. But a couple of things that we talked about in the class, in the series earlier, we talked about the hello timer and the dead timer. So this is what I can see, what this interface is using for hello and dead timers. The network type, this is where we get into networks that are non-broadcast or broadcast. This is a point-to-point. We're not going to do a DR election there, but I'll just point that out for now. Cool. This is showing you how often it's sending the hello. So if I just copy this command and I do it over and over, notice right in here, you'll see this guy is gonna count down if I keep pasting and pasting and pasting. So cool. So right now, router 1 is sending out hello packets in hopes of discovering router 2. Now, router 2 hasn't configured anything OSPF yet, so router 2 isn't responding. But just to show you something different, I'll do show IP OSPF neighbors. This is going to show you the neighbor table for OSPF. And you'll see at the moment, it is currently empty. It's going to remain empty until I configure the same thing on router 2. So just to show you, show run. This is what I've configured so far on router 1. And I'm going to configure the same on router 2, but I'll do it from router 2's perspective. So conft router OSPF 110. Router ID is going to be all 2s. And now the network command is going to match this serial IP, this interface IP address rather, 10.0.12.2. I'll again use the all zeros wildcard mask, and I'm going to again put this in area 0. You'll see that as soon as I hit enter, something will show up in the oh my goodness. A log message will pop up saying I now have a new OSPF neighbor. Just to show you the before and after, I'll show you that currently show IP OSPF neighbor doesn't have anything in it. But as soon as I hit enter over here, instantly you'll see that, hey, a particular neighbor ship has just formed. We went from loading to full. Remember I told you full was the happy state, that we've synchronized the database state. Router 2 is saying I've just become neighbors with router 1.1.1.1, that's router 1. And over here, router 1 just said I've now become neighbors with 2.2.2.2. And if I do this command again, show IP OSPF neighbor, you'll see that I am currently in full neighbor adjacency state with router 2. And I could do the exact same thing over here, show IP OSPF neighbor, and we can see that from router 2's perspective, it is a full neighbor with router 1, and vice versa for router 1. Cool, Vlad. Glad you enjoy the color. It is a pretty color, right? I kind of picked it randomly, but I do kind of like that teal. Okay, cool. All right, so we looked at the neighbor table. That's actually this command you see right here, show IP OSPF neighbor. And we see that in this command, I am currently neighbors with router 1, and I'm currently in a full adjacency with router 1. So that's looking at the neighbor command. What we didn't look at is the topology table. So to see the OSPF topology table, again, which is everything OSPF knows about, the command you want to use is show IP OSPF database. So here's the command that I ran, and right now the OSPF database has 2 entries. A router LSA for router 1 and a router LSA for router 2. Now again, we're going to unpack in more detail what each of these LSAs are. For now, I just want to show you that we have 2 entries in the database at this moment. If I do a show IP route, notice I don't have any routes that begin with the letter O. Oops, let's go up a bit, right there. OSPF routes have this letter O in front of them, and notice at the moment I don't have any. I don't have any because both of our routers, even though they're doing OSPF with one another, already know the link between the two as a directly connected route. Excuse me. The link between the two is right here, and you'll notice they both know. They both know of that network as a directly connected route. So OSPF knows about the network, but there's nothing for OSPF to add to the routing table of the router because they each know about that route. You'll see that that's going to change when I add these additional networks to OSPF. Cool, so that's the routing table. Areas, there's nothing really we're going to talk about here because everything's an internal backbone area since we're only doing everything in area 0. We'll unpack that in more detail later. We'll show, okay, cool. And I'll show you these later on. Okay, sweet. So let's add these networks. So let's start with router 2, and I'm going to add these networks, 10272, 10282, and 10292. So show IP int brief exclude UNIS. These are the new interfaces that I mean to add. Just to show you the before and after, if I do a show IP route here, you'll notice again, no OSPF routes on router 1. I'll go in here, router OSPF 110 network. Now, instead of adding these one at a time, what I'm going to do is use a wildcard mask that includes everything that starts with 10.2. This will add all 3 of these networks in one go. I'll put them in area 0. As soon as I've done that, remember I told you OSPF is very, very quick. As soon as I do a show IP, oh, had to prove me wrong, didn't it? Had to prove me wrong. Not as quick as I thought, I suppose. And here you see the new routes that were learned from router 1 for the networks on the other side of router 2. If I go over here and do show IP protocols, you'll see this is the new network that I'm currently that is currently added to router 2's OSPF configuration. Yeah, and that's it. From here, I can actually ping any of these. So ping 10282, and you'll see that they have connectivity. So now I'll do the same on the other side. If I go over here and I do show IP route, you'll see currently there are no networks learned by OSPF because, again, router 2 hasn't learned anything new. It already had a directly connected link for all of these and all of these. Actually, there is something new I want to show you. If I go to router 1 and do show IP OSPF database, this is again showing you everything that OSPF knows about. And this probably looks very similar to what you saw before. Again, we have 2 entries, one for router 1 and router 2, but there is actually a slight change. That slight change is right here. Notice router 2 currently has a 5 in its number of links within this LSA. If I scroll back up to where I showed you the database earlier, actually I think I showed it to you on this router. Yeah. Notice router 2 initially only had 2 links, and then we added the other 3 networks over here. Now you see the 5 links. So something did change in the OSPF database. And in fact, if I look at the details for that particular LSA, you'll notice here are the new networks that router 2 just shared with router 1. Now, we just went pretty deep into the router LSA, which is the type 1 LSA. Again, I just wanted to kind of give you a teaser for what to expect for later on. We're going to explore that in much, much more detail later on in this series. For now, this was just a teaser. Yeah. And then the other thing I did want to show is that the databases are indeed synchronized. Show IP OSPF database. Notice even the sequence numbers and the checksums are 100% identical. Remember, link state, OSPF will synchronize the databases completely. So everything is identical to each other. Cool. Now, the last thing I want to show you is the actual packet capture. So if I go into router OSPF 110 and I shut down OSPF, and I do the same thing over here, CompT router OSPF 110, and I shut down OSPF, we're going to come in here. I'm going to start to capture on the link between the two. And what we're going to do is essentially turn on OSPF and look at the actual packets that are being sent across the wire. So let's make this OSPF. Cool. So we're just going to filter for OSPF packets. Yeah, and then we'll turn it back on. So I'll come down in here. OSPF neighbor. Make sure everything's cleared out. Cool. No neighbors on R2. I'll do a no shut. And what you're going to start to see is router 2 is going to start sending out these hello packets. Notice the source is 10.0.12.2. That's router 2's IP address. Bigger. That's router 2's IP address. Notice the destination is 224.0.0.5. That's that multicast address that is speaking to all routers. Now, at the moment, router 1's OSPF process is still shut down. So router 1 isn't sending anything. It's just router 2. Yeah. Oops. Cool. So let's take a look inside that hello packet. And again, inside the hello packet, we told you a bunch of things that exist. One of the things we mentioned was the network mask. Was in there? The hello interval, that's in there. The dead interval right there, that's in there. The DR, the BDR, that's the designated router, backup designated router, and the priority number, that's also in there. And tell you what, we'll actually make sure we get to everything. The router ID, that's right here. That's in there. So I showed you the router ID, showed you the hello, showed you the dead. I'll show you that. The area ID, this is telling you we're in area 0, which is the backbone area. Cool, so that's right there, also in the hello packet. Authentication, we're not currently doing any authentication, so you'll see that as null, nothing included there. The network mask, just saw that right there. Cool, DR, BDR, area type, that's actually in these flags. Without getting into too much details, this N bit is telling you whether we're NSSA area, and this E bit is telling you whether we are not a stub area. So we are not a stub area. This is a normal area. But that's where that information is communicated. So that is indeed everything that I showed you in the hello packet. So again, that's all there in Wireshark. But now we want to turn on OSPF for the other router. And then we're going to see that the neighbor adjacency process. Now, before I do that, I'm going to go to router 2, make this guy a little bit bigger. And I'm going to turn on some debugs. Debug IP OSPF adjacency. And that'll be it. So these debugs are going to show you live what's happening with OSPF. And you'll notice if we wait a second, you'll see that there's a particular packet being sent out from router 2's interface to this IP address. It is a type 1 OSPF packet. That's a hello packet. In fact, if we come back over here, OSPF version 2, packet type, right there. Message type 1, that's a hello packet. As soon as we turn on OSPF on router 1, you're going to see a bunch of spam show up here. We're going to look at some of it. We're not going to look at it in too much detail now, but what I want to see is actually the packets, the new packets that show up. So again, I'll do a no shut. I'll come down over here. You'll notice a bunch of stuff just happened. Yeah. So notice all in here is just router 2 sending out empty hello packets, right? Saying, hey, I want to do Neighbor. This is where we first turned on OSPF on router 1. And here is where the router 1 started the OSPF adjacency process. Cool. So the first, like this. Notice right over here, after the BDR, you see nothing. This is the first hello packet that was sent by router 1. Notice in the next hello packet, we now see something in the hello packet. We see the active neighbor field. This was that neighbors field that I told you about in the lesson, where router 2 is saying, I see router 1 on this particular link. That kicks off router 1 sending some database descriptor and a hello packet, which now includes router 2. So now they essentially see each other, and they've confirmed it to each other by showing you the hello state. Sorry, by showing each other's router ID in the hello packet. If we go in here, I'm going to turn off the debug. So at this point, it's just a bunch of hellos being sent. We scroll back to the top. I don't want to unpack this in too much detail at this point, but just to show you some of the neighbor states we talked about, notice over here, as soon as two-way communication was confirmed, router 2 says we are currently in two-way state, and we're sending some database descriptor packets. Notice in here, router 2 is not the slave, is the master. So that's a problem that happens in the X-start, the master-slave negotiation that happens in X-start. And then let's see if I see exchange somewhere. There's the exchange state, right, that we talked about. And there's the we are currently synchronized, we are currently in full state. So that's showing you, proving you, if you will, some of the neighbor states we talked about in the course. Any case, coming back down in here, let's make this a little bit bigger. So here are the hello packets that are being sent to each other. Notice after that is some DBD descriptor packets that are being sent. And then after that, you have a link state request being sent by router 1. Inside this request, if I actually look into it, you'll see it's asking for a particular LSA, and we'll unpack the LSAs in great detail later on. Router 1 is asking for this LSA. Router 2 is providing the LSA in a link state update. Notice inside the link state update is the actual router LSA, and then inside that is all the networks that router 2 knows about. And then they're confirming the reception in these acknowledgement package. So you'll see it follows the sequence that we went through in the lessons. Cool. And I think that is everything I wanted to show you guys. So we showed you some states, we showed you the hello packets. This is a single area, so there's nothing area-wise to show you. We showed you the packets and then the neighbor tables. And I think that's it. That is all I wanted to show you guys and run through in this particular demonstration. And that actually wraps up the plan for the entire day. So let's go back over here. Cool. That's it. So this went a lot longer than I expected. I was thinking it'd be an hour, and we are 2 hours and 20 minutes into the stream. The first 15 minutes of that, of course, was just the countdown clock. But in any case, 2 hours into it, how do you guys feel? How do you guys think that went? Was anybody? I mean, I'm sure some of you kind of came in and out, but was anybody with us the entire 2 hours? Was anybody with us from start to finish? Definitely mention something in the chat if so. Yeah, and then also regarding the demonstration, what did you guys like about the demonstration? What did you guys not like? Was it too much information, too little information? Mention something in the chat room. Let me know how it went. And if you're catching this on the replay later, I still want to hear your feedback. So mention something in the chat room. Sorry, in the comments if you're catching this on replay. Cool. Awesome. Well, I'm glad you guys enjoyed it. Glad that was useful. Thanks for sitting through it. The plan then for me is I'm going to take all those lessons, kind of polish them a little bit, and then record them as formal videos. I'm hoping to go through the entire OSPF to a practical, productive, engineer level understanding, all in like 5 to 8 minutes lessons. So there'll be a bunch of different lessons, each of separate videos, and the plan is for that to happen. What I'll probably end up doing, so this is the first, what I said, 6 lessons. I'll get those recorded, get those published, and then I'll start working on the next 5 to 8 lessons or so. That'll be the next, I guess we'll call it module. And then maybe I'll do another live stream to talk through some of that stuff live, if that's something people would be interested in. Either way, I'm not seeing... Yeah, Ward, so once we get into understanding the full scope of what is inside the link state database, that'll become more and more apparent. You'll actually see that each router knows everything about the entire topology. Oh my goodness, you stayed till 12 a.m. Thank you so much for hanging out. Hopefully you got a lot out of it. Cool. So before I let you guys go, yeah, I got to do the the plug, of course. If you guys aren't subscribed, please do. I try and create very practical, very efficient learning content for you guys. I don't like wasting time in my lessons, and I value your time. And so this is the live stream, so this is meant to be live. But in the actual lessons, I try and limit the lessons to just the core of what you need to be a practical engineer. My goal is always to make you a practical engineer, right? That's the whole networking, practical networking. That's the whole brand, if you will. So definitely check out some of the rest of my content. I do have a Discord channel. If you guys want to join, you can see the link right there. You can get to it at pracnet.net/Discord. Come hang out, come say hello. Let me know what you guys think. Yeah, otherwise, like, subscribe, all that fun stuff that I have to beg for because I'm in the YouTube world. But all that stuff does actually help in promoting, getting YouTube, convincing YouTube that this is a video worth showing to more and more people. So if you think that is the case, a comment, like, all that fun stuff, and watching things all the way through to the end, all that helps with the algorithm. Cool. I'm going to hang out in the Discord for the next 30 minutes or so. If there's any follow-on questions or you want to say hi or say whatever, so please join me in the Discord. Again, you can get there at pracnet.net/Discord. Otherwise, thanks for hanging out. Hopefully you guys got a lot out of this. And if you're catching this in the replay, I still want to hear your feedback on how it all went. I'll probably be recording all this maybe this weekend or maybe the next few days. Yeah, and I guess that's it. Hopefully you guys got a lot out of it. And I'll see you guys all in the Discord, pracnet.net Discord to get there. All right, appreciate y'all. Have a wonderful rest of your day. I don't see any other questions that I missed. Cool. Yeah, again, appreciate you all. Thank you so much for joining. Have a wonderful rest of the day, and I will see you guys all in the Discord or the next video. Be well and take it easy. Bye.